All right, so let's get into 6.8, tidal streams and currents. I don't know if you've ever had a chance to experience this, but we were just in the San Juan Islands up in Washington State, and it's for real. You know, it's just the islands are such, and if we take a look at the next set of figures here, you know, as the tide is moving back and forth through these channels, I mean, it's like paddling upstream or paddling downstream. You get a real flow through some of these little features. So rather than building the barrages that we've been talking about previously, one might envision a technology, and I'm just going to jump ahead, like this, where you've just got some kind of little generator with a propeller or an impeller device attached to it. Something like this. Here are dual impellers on sort of a whale-shaped technology. Here's another one that hydroplanes just sort of flops up and down, more or less like a dolphin's tail that instead of driving is driven. Love looking at these things. Here's that particular technology. Here's a different embodiment, Rotec engineering, where you've got a horizontal axis. I'm guessing this one here is going to be a little more fish friendly. You might imagine Nemo coming out the backside as sushi on that one. The Neptune. Oh, so this is also a turbine, but a vertical axis turbine, like a squirrel cage type turbine. Another one closer to the bottom. Some others, all kinds of fun. This one designed to sort of be optimally placed in the stream and then serviceable. Another one that still allows for shipping to occur. This guy does a nice job on the graphics. And then this one, if you've looked at if we've studied Bernoulli's equation, in fact, maybe we I think we'll probably do that a little later. But if you look at Bernoulli's equation, we'll start to understand how this high velocity, low pressure zone can more or less drive a pressure gradient to run an underwater turbine. Here's another one where you've got individual little Venturi tubes driving a turbine here. So relatively little machinery for wildlife to interact with. Gets around that problem. Excuse me, another one where rather than building a barrage, you sort of have little gates. It allows shipping to occur. This looks like an actual photograph of a deployed technology. Also, these blades are going to spin slowly enough that you can imagine, okay, you're swimming past it, you get bumped, but not fatally so. Who knows though? Well, I'm sure some people know. Another concern would just be acoustic noise underwater. Of course, whales communicate with their sonar. There could be other species that this is kind of messing with their communication frequencies. Again, economy of scale. Build a couple big ones instead of a small one. This is sort of more lab-sized actual deployment. I'm just burning through these now because they're just kind of fun to look at. We'll get into some of the physics here in a little bit. Again, this is another horizontal helical blade. And one in Italy. Okay, so more blades. All right. So let's go back to kind of where we were at 6.8. Each one of these has sort of a terawatt hour per year capacity, if you will, starting up there at the Pentland Skerries. It's not in the little map there. Oh, but it is in the Pentland Firth. So right around the top, there's sort of more. And again, this is going to be just a function of what the topography looks like. How much of a pinch point there is. You sort of look at this island and can appreciate that. Gosh, the tides that are more or less trying to move east to west. This big north-south impediment is going to force a lot of water through here. These guys aren't even mentioned, but with this nice tiny little pinch point, you can see why that might be a very energy dense area. Okay. Oh, you know what? I think I was on the wrong. Oh yeah, here we go. Yeah, there's the Pentland Firth at the top. There we go. Okay. On some of those technologies we were looking at before, we could see the depth of the technology is an issue. What we're looking right here is a parabolic profile of the water flow. So if and you can think about it this way. So let's say you've got a 50-mile-an-hour wind blowing past you. Where do you want to be out of the wind? Do you want to be up high? Do you want to be down low? Well, the closer to the ground you get, the less, not only is there, less total wind blowing on you, but the actual velocity at the ground surface is lower because there's friction. The air, or in this case the water, interacting with the seabed, the solid surface, causes it to do this. Now, this is also what causes waves to form in some cases. So if you look at this, this arrow actually represents the velocity of the water. So this water at the top is traveling faster than this water. Well, what ends up, that leads to swirling, right? So if this guy is going fast, this guy is going slow. So this top part's going fast, this part's going slow. It actually causes that type of little swirling. You see the same thing with the waves from the wind as well. But if you had to choose, like, hey, where do I want my technology? Well, as close to the surface as possible. So that's why we were looking at those different propeller designs being, more or less in this area without, and obviously once you get to the surface, then you're out of luck, you're not in the stream anymore, so there's going to be an optimal spot or a sweet spot there. Okay. So now we're looking at extractable shaft power, and this is in kilowatts. So the coloring might be a little bit hard to see here, but this very bottom line is 1 meter per second. And if you remember all the way back to NRGY 101, when you read the comparison of energy density, the late 2008 paper, this is where I got a lot of my numbers. In terms of, what is the energy density of tidal power, and it ends up being on the order of 5 to 10 watts per cubic meter, et cetera. These curves are parabolic because, if we go back again to our Energy 101, we know that kinetic energy equals 1/2 mv squared. So that's your velocity squared. That's why those are parabolic. If you take that for tidal, it's going to be 1/2 rho v, which is volume squared. So this just means that the bigger the technology is, the more energy you're going to get from it. This obviously means that if you have a more dense fluid, not that you can affect the density of the fluid, but it also tells you that, gosh, for water that's 1,000 times more dense than air, you're going to get a little more bang for your buck. The other thing to notice, though, is that ooh, but look at the velocities. 1 meter per second, 4 meters per second. That is very low compared to what you get for wind, right? So what you gain in density, you lose in velocity for these technologies. Okay. You know, and I like the cuteness of this guy. It's something that, you know, you stick your anchor in, you put the cable in, you pop it out there, and up lights the buoy. And this is, you know, relatively simple, relatively easy to move if you need to. You know, the question is, where does the electricity go? is maybe one question. You're just lighting a light. Well, looks like they've got a little bit of, it's a safety feature, you know, so it's telling the ships where not to go. And it could also be a GPS. You could also imagine, if you've been following lately, the University of Montana just got one of these X Prizes for developing a ocean-based CO2 sensor, so sensing CO2 absorption levels in the ocean. You could stick one of those on there, and it sends out what the CO2 levels on. So, you know, there's a variety of technologies you could imagine putting in there.
How much CO2 does water absorb? Isn't it something like 2% or something?
Well, that's a good question. How much CO2 does the water absorb? As much as it can, you know. And the way to think. I mean, I don't mean to be a smart aleck about it, but you obviously drink, had a soda to drink, right? And so when you open that can of soda, the bubbles come out. Right. And so under pressure, that CO2 is more or less been forced into the fluid, and it's sort of everywhere, but nowhere at the same time. When the cap gets open, the pressurized energy is released. Every single material, gas, liquid, solid, or any substance on the periodic table is going to have a boiling point, a freezing point, etc. And this is a long answer to your question, but you could imagine CO2 saturating at the ocean's surface, being taken down deeper into the ocean through the thermohaline thermohaline convection. Those bubbles compress, and then depending on the dynamics at the bottom of the ocean, they could come back up as bigger bubbles. You've heard of divers getting the bends, where your blood essentially boils and nitrogen comes out. Similar concept. So there's no one real answer to that. I mean, the ocean will absorb as much CO2 as it'll hold. The more CO2 there is in the atmosphere, the more that gets forced into the ocean. It's just as simple as that. It's like the more that's in the atmosphere, the more ends up in your lungs every time you breathe. In fact, one of my buddies sent me an email saying that it appears as if it might be starting to affect our cognitive abilities. Because at some point, I mean, nobody wants to sit around breathing their own CO2, right? I mean, you can probably breathe in the bag and I feel a little dizzy here. So, yeah. But anyway, that just, down the rabbit hole a little bit there. But you can imagine one of these systems being a good way to measure the amount of CO2 remotely. Okay. So the CGen, this is obviously an actual technology. Northern Ireland, 2008, 1.2 megawatts. That's at a tidal flow of 2.4 meters per second. That's faster than you can swim, by the way. So it's honking along pretty well. It says that CGen has proved successful delivering power to the grid, earning renewable obligations, certificates, et cetera, et cetera. Good. Okay. And I think we've already gone through a lot of the novel designs. There are all kinds of ways to get things to wiggle, spin. Nature's been doing it for years in terms of propulsion. We're now catching up with that. Just going to kind of flip through these again quickly. Yeah, there's not a... Yeah, this guy can, rise and fall with the tide. Again, to get in that sweet spot. There's no limit. There's no limit. Canada, India, Blue Energy, 2011. I do know. I do have a friend who owns a company called Acilla Power in Seattle. So if this is the type of thing you're into, I do have a few colleagues in this field. I'd be happy to introduce you to them. Yeah, I mean, there's really not a heck of a lot else in this chapter. So I think read through it. We covered the economics. We covered a lot of the novel technologies. We covered, terawatt hours per year, all kinds of different shapes, big, small. There's a mention here that the kinetic energy of the Gulf Stream has 65 gigawatts. So as soon as we're ready to tap that guy, it's sitting there waiting for us. There's a deal on Sicily. I like that one. And and these projects, I mean, they have the lifespan of these have the lifespan of what of the continents, of how much longer before Sicily collides there with the rest of Italy. Probably quite some time. So that these are projects that I see being very viable into the distant future. The Bay of Fundy is mentioned here. That's one of the more famous bays in Canada. That's on page 288. Bay of Fundy, giant fluctuations. Yeah. Yeah. I'll just read this last little bit here. Tidal current assessment. This is on page 291. It says, although tidal barrages offer larger amounts of energy per project, and tidal current technologies in its infancy, at the time of writing, the prospects for the latter look more promising. It says tidal current systems may also be easier to develop than the wave energy systems of Chapter 8, whereas wave energy systems have to operate in a chaotic interface between air and water and have to try to capture energy from multiply vectored wave motions using complex technology. Tidal currents are smoother, we knew that, laminar flows in a much more stable, although still turbulent undersea environment. And the energy can be captured using relatively simple turbines. So it's not surprising that given the relatively easier technological challenge, tidal current projects have proliferated. 2011, there were 100 different devices under development around the world, various scales. Few, that's kind of discouraging, few are likely to be commercially successful, but those that are may reap large rewards. That would be fantastic. One study suggests the annual world market for Tidal might be as large as 155 to 444 billion pounds. And as we saw, the UK is in a great spot to harvest a lot of that. It says, however, it's unlikely to be possible to harness all the sources, and certainly it could be time to do so. The DTI Carbon Trust Renewables Innovation Review put UK at 31 terawatt hours per year, or 10% of UK electricity demand. The Carbon Trust Taking Economic put the Tidal figure at only 18 terawatt hours per year. I think, you can't help but be confident that carbon is going to have some kind of price on it, and that is going to go into the bottom line on these projects. I also want to let you know that there's some other giant projects happening right now. Elon Musk is open sourcing this Hyperloop project in California. The idea is to build a solar-powered, evacuated Mach 1 train system between Los Angeles and San Francisco. And projects at that scale, and the ones we're looking at here, what's the point of all of them? Well, the point is to allow us little ant people on this giant planet to have, warmth, shelter, movement, nourishment, et cetera, et cetera. And so by, investing in clean technology, clean, fast, efficient technologies now, we're ensuring that for future generations. And, I really hope, and I can't help but be optimistic, that the world is going to wake up and get it and say, time to, literally reinvent fire, like Avery Lovitz has been talking. The other thing I want to mention about Musk's Hyperloop project, and this project really could drive the new world economy, and I'll tell you why. I haven't fully wrapped my head around it, but I'm starting to get involved with some engineers who are. Elon Musk Solar Rail Project. So if you look down here, it's kind of funny. I've had a guy in my office over the past couple of years. It's been a while since we've talked. He's, got some great ideas, but, no funding, no, et cetera, et cetera. I'm like, okay, let's keep talking, but it was, sorry. He wanted to build a bullet train between the Bitterroot and Missoula. Just use the Bitterroot rail, very, similar concept where you're in a little tiny pod. You're not driving, but you're going really fast. So whatever you lose in your sense of security and claustrophobia, et cetera, you gain in the fact that you got to your office in 3 minutes from your living room down in Stevensville or whatever. But let me show you the economic model.
You can ride it if you want. You can wait for me at the other end.
Let me find, I read it here, let me just find hours. Oh, okay. So it says from 2012 to 2013, an informal group of engineers worked on the conceptual foundation, allocating some full-time effort towards it in the end. Musk invites feedback to see if people can find ways to improve it, open source design. It sounds like what he's doing, no one's really getting paid for this per se, but the hours logged for each person are being tracked. So obviously this system will have some value. They talked about, a $20 ticket or whatever to get from point A to point B. And so again, going back to this figure, you put your time and your money in up front, and the idea is you get it back over time with tickets. Same deal on the project. And so what so a new mode of collaboration, and maybe it's not that new, but a mode of collaboration now that I'm starting to see emerge is where you have large groups of people working on a big engineering project like this, and not any single one person can do the whole thing. And like imagine trying to build a laptop computer by yourself from scratch. Ain't gonna happen, right? There's so many different steps, little processes along the way. Some of which people never touch, all of which we've designed, but the value and the payback comes back later. And so you can sort of think of putting your time into a little time bank now in the design, and then you've got that as a share, and so the thing has some value, and who gets it back? Well, who put the effort in up front. So that's really all I wanted to say about that. And then there was one other, so just seeing some of these large Tidal projects really made me think about Musk's very large, very ambitious project, and I know that we're going to see very similar large-scale things happen with other energy tech, and he would really like to have this thing be zero carbon, where it's just powered by solar power. I'm not sure you could take it completely off grid, but I also know that California is moving towards installing 1.3 gigawatts of storage, and you could even think of this train as maybe being some energy storage too. I mean, it's probably mostly friction, but at some point over its path, as it's going downhill, it actually might give some back in terms of regen braking. I'm not sure, but I'm sure that's all kind of under consideration. I was trying to think of a similar concept for solar-powered train in Montana, where, you don't want the thing to go too fast. You'd really want some regen braking on the downhill, recharging your batteries or what have you. So, okay, 4 o'clock. I think we're about done. Is that right? 4:30? Huh, well, I'm done. I'm done. Unless there's anything else you want to talk about, summary 3 or problem sets or anything, I'm happy to